Folks, welcome to Chemistry 251. This is Organic Chemistry 1, and it's our first lecture module together. Isn't that sweet? And in this first lecture module, we're going to talk about the concepts of general chemistry, and it's meant as a review. So, if you're learning things for the first time during this part of the lecture module, then don't blame me. Blame your general chemistry instructor, because they should have went over this with you wherever you took it, whether it's here at Cape Fear or someone else or somewhere else with someone else, right? Okay, so in this lecture, I know people are going to come to this class with different backgrounds. They've taken chemistry at different times. They've taken chemistry at different universities or different colleges maybe. And I know that the background is going to be blended. So guess what? If you did not pay attention in general chemistry, it's okay, because we're going to go through the same concepts all over again with this lecture module. So that way everyone can be on the same foundation, because these are the things that are important for organic chemistry. And if you miss out on these topics, you're probably going to miss out on organic chemistry a little bit later in the semester when we get deeper and deeper into the field. All right, so what you're seeing on the screen right now is a meme, and it says, "Welcome to Organic Chemistry," where questions like, "Where do you keep your chloroform?" are no longer suspicious. That's right, folks. These types of solvents, these types of chemicals, it is a brand new game for us. It is nothing like general chemistry. Quite often, if you want my honest advice, general chemistry, people that do really well in it go into organic chemistry thinking they're going to do well in this class, and they don't, because it's not the same game. General chemistry and organic chemistry are different. General chemistry loves equations, loves mathematics, loves numbers, loves you to use the calculator. Organic chemistry is all about how it makes you feel. What does it look like? What does it sound like? What does it smell like? How do these two things come together and make a product? That is totally different than the general chemistry that you have taken up until this point. And throughout this semester, hopefully, you're going to realize that. All right, so what I want to do first is just to kind of clarify, what have you gotten yourself into? Right? I mean, we're in organic chemistry, so I think that we should kind of clearly define what the term organic actually means. Don't you? All right, well, there's a story here, and this story is in general chemistry. You've learned that there is a classification called inorganic, and then there is a classification that's called organic. And you might have went through the motions of labeling something as inorganic or organic. And you looked at the structure in order to determine this. Well, by definition, organic chemicals and organic chemistry, well, it's something that we call carbon-based. Carbon loves organic chemistry. That is what we focus. That is what we center our studies on. Carbon. And carbon can bring with it some buddies. And those buddies, of course, can be hydrogen. Sometimes they're oxygen and sulfurs and nitrogens and phosphorus, but very few get into carbon's special club. All right? Well, the inorganic side of the house, the inorganics are compounds that don't really involve carbon. It's all of the other people that didn't get into carbon's club. Think of carbon as the celebrity, and think of us as everybody else. We're not a celebrity. We're not in big shot movies, right? We're not singers. We're not in carbon's club. So we're the inorganic chemicals. Those celebrities, the special ones, they're the carbon-based ones, and those are the organic chemicals that we are going to be studying throughout this semester. All right, well, this story actually goes back to a researcher with the last name of Berzelius. And Berzelius, in the very early 1800s here, actually labels this classification for the first time. Two different types of material, inorganic and organic. But these were not the definitions during that time. Berzelius did not use carbon-based or non-carbon-based. Berzelius used a different definition for each one of these. And it looked at life. So for instance, you are a living person. If you make compounds, and if you excrete some of those compounds, might be in your pee, right? Then these compounds are going to be dubbed as organic. It's coming from a living organism. All right, well, if you did not make these compounds, and they never really show up, they're just out there in Mother Nature somewhere, then this is what we would call inorganic compounds. But this was way, way back. This was in the 1800s. Berzelius has this classification. If it comes from a living organism, the compound is called essential to life. And that is what we would deem an organic compound. If it didn't come from a living organism, it wasn't essential to life, therefore it's classified as an inorganic compound. Well, here's Berzelius. If you ask me, he reminds me of maybe the Hamburglar or Grimace from the McDonald's drive-thru, right? And if you're an 80s kid, you'll know exactly what I mean. But Berzelius, even though he doesn't look quite happy here, did some pretty major things back in the day. I mean, he was very popular. He worked with Alessandro Volta, and he started this whole theory of voltage and what it can do to chemical compounds. Well, he basically put things like water and applied voltage to it. And water was actually decomposed. We can separate these compounds into H2 and O2. Well, you learned about this in general chemistry. We called this a decomposition reaction. Well, this was kind of what Berzelius was playing around with back in the day, when he was discussing this organic and inorganic type of classification. So he played a couple of major roles in science along the way, and he was also known for chemical symbols. So you can thank him for what I've just wrote on the screen. Your H and your O and your H2O. H is hydrogen, O is oxygen. He played a role. He wasn't the only one, of course, that did this, but he did play a major role in chemical symbols and what that means. All right, so here's a face to chemistry. And this is something that some instructors don't ever mention. They don't ever talk about. They don't show you the faces and the people, the men and women behind the whole field. And I think that's important sometimes, especially when we're so bogged down with equations and numbers, calculations. This kind of breaks it up a little bit, at least I hope. All right, so there's Berzelius. Thank him for the definition of inorganic or organic. So this whole concept of vital force comes around. Vital forces, well, here's a quote. You can take the phrase, you can live on nuts and berries, but you can't live on dirt. Okay, so what does that actually mean? Well, there's things that we need in order to function every day, right? And this is where the concept of vitalism comes into play again. So this whole concept of organic chemistry back in the 1800s, right? We can go out and we can eat nuts and we can eat berries and we can survive on that type of stuff. That's foodstuffs for us, right? But we can't eat dirt and we can't eat rocks. We probably could, but it wouldn't taste very good and it wouldn't be very comfortable when it goes down and it wouldn't be very comfortable when it comes out. Okay, so there's a major difference here, right? There's a major difference between what a nut and a berry can do and what a rock and dirt can do. So this is why, and you can easily see why now, that they made this decision back over 200 years ago. What is the difference? There's got to be a fundamental differences between the compositions of these items. Why is it that my body can respond to one group of things, but my body cannot respond to another group of things? So that one group of things that my body does respond to, we're going to call that vital force, and we're going to call that organic, because it's living. Living bodies need it. On the other side of the house, my body doesn't respond to it. I don't need it. It's not essential. It's not vital. So we're going to call that inorganic. Well, the story gets a little bit more complicated here, folks. So this was accepted, this essential to life definition. That was accepted many, many years until we have another researcher. And that other researcher goes by the name of Wohler. W-A-O-H-L-E-R. Wohler. All right, well, Frederick Wohler, about 1830s, give or take a little bit. Okay, we're rounding off. Dates don't really matter here. We're just giving you a quick background and storyline. But in about the 1830s, Frederick Wohler comes through and he says, whoa, wait a minute. I think we've had this wrong, people. Because I've just made an organic compound. Now keep in mind, organic was thought at one point to only be made by your body. And now we have a person that made a compound that was thought to only be made by someone's body or life. Okay, well, we have a fancy term that we talk about, that we use in substitute for made, we call synthesize. And this is a very important term in organic chemistry. We're going to be talking about how to synthesize multiple different compounds, folks. So this is a word that we're going to be seeing over and over and over and over. And by the end of this class, you're going to be thinking and dreaming of synthesis steps. At least I hope not. I hope I'm not driving you that crazy by the end of the semester. But who knows? Maybe. Well, Wohler comes through and says, you know, this is not really going to be an acceptable definition anymore. Because now I can make an organic compound that we thought was organic up until this point, and I can make that in a laboratory. What exactly did he do? All right, well, he took a compound, and I'm going to go all chemistry on you for a minute. He took a compound, and this compound was called ammonium cyanate. All right, ammonium cyanate, NH4OCN, and he ended up making a compound that we call urea. And that urea is a carbon with a double bond oxygen. And on each side of that carbon, we have an NH2 group. All right? That's what it was all about. That was it. How did he do it? He added some heat. That was all. And of course, the triangle is a very short-handed notation for heat energy that we like to use in laboratory sciences, especially in chemistry. Well, what's going on here? What's the organic compound? The organic compound's urea. Well, why is that labeled as an organic compound? Because urea is a major component in urine. So every time you go to the bathroom and you pee, you're peeing out a solution. And that solution's made up of a number of things. And part of that is what we call urea. So Wohler goes in and he says, listen, guys, I've made urea. Eureka. That means that your definition of organic is not going to hold true anymore, because I've just made something that was previously thought to only be made by living organisms. So Wohler actually goes through and completely demolishes this concept of vitalism. No longer is in existence anymore, because Wohler just proved those guys wrong that made these definitions up about 30 years prior. And this is what begins the concept of organic chemistry. Very often we talk about fathers in sciences because for the most part it seems like men are always given the credit back in the day, hundreds of years ago. So we often have these fathers associated with the sciences. Wohler could be regarded as a father of organic chemistry because he really did the first synthesis step that proved you could make an organic chemical, and this organic chemical is still regarded as an organic chemical today. Remember, I said it's carbon-based, and carbon brings with it some buddies. And those buddies could be some nitrogens or hydrogens or oxygens, but very few of them. And you'll learn who those buddies are as we go throughout this class. On the other hand, ammonium cyanate, NH4OCN, this really isn't an organic compound. And you're probably going to look at this and say, well, why not? There's carbon, and carbon's brought with it some buddies, nitrogens and hydrogens and oxygens, just like you said over here on the product side. Well, yeah, that's true. It is carbon. Carbon did bring some buddies to the party, but this is not regarded as an organic chemical. So now you know the definition of organic has to be a little bit more complicated. Well, the reason ammonium cyanate is not listed as an organic compound is because truly this is an NH4 that has a positive charge and an OCN that has a negative charge, and we regard this as a salt. And a salt is always classified as inorganic for the most part. All right, so I'm getting a step ahead of myself at this point. If you did not know that, no big deal, no problem. Just bear with us. We'll eventually get to those descriptions. We'll eventually get to that part of the lecture. Just kind of sit in, get comfortable in your seat, and enjoy the ride that organic is about to take you on. So this is where I'm going to stop this video. And in the next one, we'll talk a little bit more about Wohler, a little bit more about the production of urea, and we'll kind of see how it fits this whole narrative of what organic chemistry actually is.